Okay, here we go. So what we're going to talk about now is more stuff having to do with vectors. Okay, so let me put to writing mode. Cool, there we go. So today we're going to learn about something called the dot product. And the dot product, so actually let me rewind a little. There are two types of multiplication with vectors. They haven't gotten back to me on it yet. Person who asked about the tech support on the question. They have not emailed me yet. So sometimes it takes like a couple hours to a couple days. So anyways, there are two types of multiplication with vectors. One of them you've learned about is scalar multiplication. Scalar multiplication is a scalar times a vector. Okay, so you could have like the scalar r. Okay, that looks ugly. What the hell? You could have the scalar r times the vector v. Okay, so the scalar would be that part. The vector would be that part. And we can rewrite this in component form. You have some number times, I don't know, x1, y1. Now, how does scalar multiplication work? Like, what do you do now at this point with scalar multiplication?
You just put it inside.
Awesome. Yeah, you distribute the scalar. So what you get is the scalar times each of the components. This is like a vector from R2. Oh, and the way you say that a vector is from R2, you write your vector, and then you write this little thing, it's an epsilon, and you say R2. So this means literally that the vector v is two-dimensional. The funny thing that looks like an E is an epsilon. Okay. Now, from a geometric perspective, what does multiplying by the scalar do? Like, what is the difference between the vector v and the vector 5v?
Five times that vector v.
Yeah, so scalar multiplication changes the magnitude, right? It does not affect the direction. So scalar multiplication affects only the magnitude, i.e. the length, not the direction. Because like as I said, if this is your vector v, your vector 5v has the same starting point, same direction, but is 5 times as long. Or actually, let's put them side by side. Let's draw it like this. So if this is your vector v, your vector 5v is parallel to that, but 5 times as long. Okay, so I've already learned about one sort of scalar multiplication. Oh, sorry, we've learned about one type of vector, one type of multiplication for vectors, the scalar times the vector. And actually, my bad, there are 3 types. Okay. So what are the other 2 types that we're going to learn about? The other 2 types are called the dot product and the cross product. Product being another word for multiplication. These two types of multiplication are vector times vector. And there's actually a really interesting historical development to all of this. Oh yeah, I can scroll up. Is that good? Is that what you wanted to see? There's actually a really interesting historical development to all of this, because like basically 100 and 150 years, well, about 150 years ago, when people were pioneering all of this, they basically got in big arguments about like, oh, the real type of vector multiplication is this one. They didn't call it the dot product yet, but like people like swore by saying the dot product is the real one, or the cross product is the real one. There's a bunch of people who invented this stuff. One of them was Josiah Willard Gibbs. He was at Yale. He was one of the people who was the founder of what we now call vector calculus, which is what this class is about. There was another guy in Ireland. He invented something called the quaternarians, which are a different type of vector, very related to the things we're talking about. He invented the cross product. I can't remember his name. But basically, at the time when they were figuring all this out, they thought there could only be one type of multiplication, and it led to a variety of interesting discoveries about how to think about vectors and what they were. And if you're interested in this stuff, this all falls under what is called linear algebra. So this is a short introduction to the field of math called linear algebra. There's another class that you could take about this at here. Yeah, exactly. What class is it? Yeah, 103. So in 103, you actually go through like more of the fundamentals of how this works with different things, and this linear algebra and all this ends up being used in differential equations. It gets used a lot in engineering and physics. So there's a lot of cool stuff going on here, and a lot of very interesting ideas, a lot of time spent discovering them. It's like 100 years of work. So if you're interested in this sort of stuff, linear algebra is what you want to pursue after this. Okay, so let's get back to the dot product. So let's define the dot product. So definition. So let's do this in 3 dimensions. Let's say that you have the vector u with components u1, u2, and u3. So what sort of vector is this? Yeah, spans of R3s of vectors, yeah. Sure. All that stuff's really cool. But what sort of vector do we have here, everyone? See if we've learned the lingo yet.
A unit vector?
No, this is not a unit vector. Sort of like when I was talking about up here. What sort of vector did I say we had?
2-dimensional?
Okay, yeah. So what sort of vector is the one I have here, my u?
3-dimensional?
Awesome, yes. So we would say that u belongs to R3. We're talking about a 3-dimensional vector here. Okay, let's have another vector v with components v1, v2, and v3. So v is also a 3-dimensional vector. It belongs to R3. Okay, so the dot product is defined to be the sum of the products of the components. So in other words, and this is how you write it, to write the dot product, you write u dot v. Okay, so the dot tells you that you're doing a dot product. Okay, so what you do is you take the components, u1, v1, you multiply them together. Then, so that's the product of a component, and then you add. So then you go to the next components, u2, v2, multiply them together, and then you add. And then you go to the next products, u3, v3, multiply them together, add it all together. So there's some interesting stuff going on here. So this is called component-wise multiplication, because you multiply the components and then you add them. Now, what do you end up with at the end? What is all of this? Like, u was a vector, v was a vector. What is u1, v1 plus u2, v2 plus u3, v3? Right, but what do you have in components? They are the components multiplied and added together. I guess let's do an example with a number with actual numbers.
A scalar?
Yeah, this is a scalar. Awesome. Thank you. So the dot product is really interesting. You dot product together two vectors. You get a vector times a vector, and the dot product gives you a scalar. So the dot product takes two vectors and returns a scalar. So the way we would actually write this in math is we would say you took R3, you dotted it with R3, and then what you got out was a number, which is just R1. And normally you would just put a comma in between them. Let's just do that. So I took two things from R3 and it spit back a number from R1. R1 is just a number. A number on the number line. So let's do like an example. Let's say that you've got the vector 3, 5, 2, and you're dotting it with -1, 3, 0. Okay, you're dotting it, so you do component-wise. You do 3 times -1 plus 5 times 3 plus 2 times 0. Now, 2 times 0 is just 0. You're going to get -3 plus 15 gives you 12. Notice, like what I was saying, you started with a vector, dotted with a vector. What did you end up with at the end? 12, which is a scalar. So if the dot product takes two vectors and gives you a scalar, what do you think the cross product will do?
Take two scalars and give you a vector.
No, because then you wouldn't be doing scalar multiplication. You'd be doing, I'm sorry, then that would not be vector multiplication. But good guess.
Would output a vector?
Yes, the cross product will take two vectors and return a vector as opposed to the dot product, which takes two vectors and returns a scalar. That's why there's that's why you have the different types of vector multiplication. There's several different ways you can put them together. Scalar times vector, vector times vector equals scalar, vector times vector equals vector. Let's do another example here. Okay, what about if you do 10i minus 10i minus 4j plus 7k dotted with, let's just do all this in red, dotted with negative 2i plus j plus 6k. So it's pretty straightforward. You take the components, 10 times negative 2 plus negative 4 times 1. Where did this 1 come from?
Front of the G.
Yeah. The j is 1 times j. And then plus 7 times 6. So you get negative 20 minus 4 plus 42. 42 minus 4 is 38. 38 minus 20 is 18. And like I said earlier, this is a scalar. Okay, so is it making sense how to compute the scalar so far? Anything you want to ask about this stuff? The hat means that it's a vector. So if you write like I with a hat, in fact, it's not just a vector, yeah, it means it's a vector. There's two different ways you could write it. You can write, you can write like V with an arrow, that means a vector. Or you can write V with a hat. Usually the hats, though, mean that it's a unit vector. So like I hat is the unit vector 1, 0, 0. Anything else you want to ask? Okay, cool. Truck along. Truck along we shall. Okay, let's, so you start wondering, after computing these numbers, what does the scalar that you get from the dot product mean? So, we're going to give ourselves a graphical interpretation. There are many ways to interpret what the scalar you get from the dot product means, but for us, we're really interested in the graphical representation of it. Linear algebra, in some sense, studies the different meanings of the scalar. So, graphically, what does it mean to dot product two things? So let's start with a picture. Let's say that you have a vector u as a starting point right here. And let's say that you also have a vector v. So let's say they have a shared initial point. U and V have a shared initial point. Okay. Now, looking at this as I've drawn it, what might you, what would you like to, what's something graphically that you can add to this little diagram with my U and my V? Just like thinking graphically. Like if you were in a geometry class, what might you put on the diagram?
Connecting the endpoints.
You could connect the endpoints. That's actually one thing that we will talk about next. What else could you do? We'll deal with the connecting the endpoints next.
The resultant?
What do you mean by the resultant?
Like projecting like U on.
Oh, okay, yeah, that's one thing we could do. So like what he's talking about is like you could like drop a right angle and look at like that vector right there, yeah? Eventually we will, interestingly enough, look at that. What else so there's like several things that we've added here. Let's write them down because they're actually all quite good.
You can also project things like starting from the end of the U and projecting like you want to do it V there, and then starting by the end of the V and try to project U and have the resultant of both two.
So, yeah, let's write those down. You can connect the endpoints. By connecting the endpoints, you could get this vector. Okay, that's one thing that we will look at later. Two, you could look at the projections. The projections mean you would drop an altitude and then look at that vector. What else could you add to the diagram? Actually, I'm just going to say it. Yeah?
I was talking about the projection starting from U, starting from the end of the U, and going straight up like V. Like you want to project V on the end of U.
Like that?
Yeah, and then you project U starting from V.
Oh, yeah. That would be for the vector addition, right? We could also do that. Another thing that we could look at here is the angle formed between them. Which we'll call theta. And this angle will actually be helpful for the two earlier things that I talked about, the projections and connecting the endpoints. Okay, so there's this angle between them. And the dot product ends up being something really interesting. U dotted with V is equal to the magnitude of U, in other words, the length, times the magnitude of V times the cosine of the angle between them. So this gives us a graphical interpretation of what the dot product is. And actually, you can solve this for cosine, and you get that the cosine of the angle between the two vectors is U dotted with V divided by their magnitude. So if you want to know the angle between two vectors, you can take the cosine inverse of U dotted with V divided by the magnitudes. And what's cool about this is that it connects graphically what's going on, like the angle, with this calculation. We're not going to prove it, but it would work. So like, let's use this to find the angle between two vectors. So let's say one of your vectors is... Actually, let's draw this. Let's put it in an axis. Okay, let's say that one of your vectors looks like this. So the vector u is 3, 1. And the vector v is 1, 2. Okay, and you're interested in finding the angle between them. Okay, so it's a pretty straightforward calculation now. Well, to find the angle, we know that we're going to take the cosine inverse of... Okay, so let's do u dotted with v. So if we do u dotted with v, we'll get 3 times 1 plus 1 times 2. And let's calculate the magnitudes on the side. So the magnitude of u will be the square root of 3 squared plus 1. Because remember, the magnitude, what you do is you square the components, add them together, and take the square root. So that's going to be square root of 10. The magnitude of v will be 1 squared plus 2 squared, which will be 5, root 5. So on the bottom you get root 10 times root 5, which means I'll get cosine inverse of 6 plus 2 is 8. 8 over root 50. Let's see, what is the cosine inverse of 8 over root 50? 1 second, I'm like opening a calculator. The arc cosine of 8 over the square root of 50 is okay, my calculator's acting weird. What the hell? Okay, 1 second. What the hell? Why is this not giving me a number? What the hell? Sorry, my calculator's like not giving me the result. What the hell? Yeah, I'm like, okay, what mistake did I make here? Okay, we've got 3, 1.
Isn't it 5 over square root 50?
Thank you. Thank you. Oh my god. No wonder. I made a math error right here. Thank you. I was like dying inside. I was like, what did I do? Okay, let's see if that works. Thank you so much. Ah, there we go. Pi over 4. Also known as 45 degrees. Woo woo! That's a 45-degree angle. Oh man, I was like going crazy. I was like, what did I do? Now, this is actually sort of cool. Somehow, we were able to calculate this number. I didn't have to draw a triangle. Linear algebra actually has a lot of really interesting applications. It's used a lot in graphics. So, does anyone know about the OpenGL programming language, or Vulkan, or OpenES? Has anyone heard of those things? Have we ever heard of OpenGL, OpenES, Vulkan? Have we heard of, and is anyone familiar with this? Have we heard these words? They're the programming language that graphics programming is done in. And when you're drawing pictures on a screen, you need to do things like calculate the angle between two stuff or do projections. All that is done in linear algebra. It's why linear algebra is usually a required course for computer science majors. It's also used a lot in physics and stuff, but there's a lot of ways that all this stuff is used. It's pretty cool. Okay, but like I think it's really interesting. Like, we drew this diagram, we calculated these numbers, and boom, we got angles out. And there's some interesting consequences to this. Can I move away from here? Can I scroll down? Just want to make sure that if you've been able to write this down, or if you have any questions about it, any of the steps. Okay, cool. So, let's talk about what this tells you. We know that U dotted with V is equal to the magnitude of U times the magnitude of V times the cosine of the angle between them. So I'm going to draw my U like this, and I'm going to draw my V like this. Okay, I've drawn them at a right angle to each other, okay? So my angle is pi over 2. So, what do you know about the cosine of pi over 2?
Isn't it 0?
Yeah. So, if the cosine of pi over 2 is 0, what do you know about U dotted with V now? What do you know about U dotted with V now? What does it have to be?
Has to be 0.
Yeah. Okay. So what about if V was like this? Or let's call this W. What's the angle formed between U and W? In other words, what's this angle?
3 pi over 2.
3 pi over 2.
270 degrees.
Yeah. Awesome. So, what is the cosine of 3 pi over 2? Oh shit, I wrote 0. I don't know. Crap. Why did I didn't even give it. I just wrote it. So I guess the better question now is, what is U dotted with W then have to be? 0. Cool. Are there any other values that you can plug into cosine and get 0? Other than these? Oh, yeah, itself. Okay, cool. Okay, so so you can draw a little right angle right here. When two vectors form right angles with each other, we call those orthogonal vectors. And what this is telling you is that u and v are orthogonal only if their dot product is 0. So like to give you an idea like why we care about this, if this is your u and this is your v, and I know that u dot v equals 0, what can I say? What can I do with these two vectors? Well, I know that I can draw a right angle between them. And what do they sort of like form as a pair, basically? Like, why would you be interested in u and v in this sort of way? Well, yeah, I mean, it forms a right angle, I said that, but like, what else do you work with that forms a right angle that like is like one of the basis of like one of the things you use in mathematics for graphing? Yes, it's a pair of axes. This is like basically the x and y axis like rotated. And for people who are in linear algebra, you talk about whether two vectors form a basis. A basis, an orthogonal basis, is basically two vectors that when you do their span, you get a plane and they're orthogonal to each other. So now, like, if you have two vectors and their dot product is 0, you could use them like one vector like this and one vector like this, and like you have like a right-angled axis. Like you still have an axis, everything's just tilted if it's like this. Hopefully you're like looking at me on the screen. Right, just imagine my two arms are u and v. Like they're still orthogonal to each other, but they've been like moved. So usually we're interested in this for a variety of reasons, which we will talk about more and more. Okay, let's keep going. Okay, so there's some rules you can use to help you do dot product calculations. I want to talk about them. So these are called the properties of the dot product. Okay, so for this example, we're going to use u and v. Let's imagine that they're vectors in R2. And u is equal to u1, u2, and v is equal to v1, v2. So let's look at u dotted with v. That's u1, u2 dotted with v1, v2, which is u1, v1 plus u2, v2. What could I do with u1 and v1? What sort of change could I make? Because they're two numbers being multiplied together, how could I change that expression?
You could say V1, U1.
Yeah, I could switch their order. I could write V1, U1, and then I could do the same thing for the other one. V2, U2. Now, do you see how, because I had U dotted with V, I ended up with U1, V1? I've switched the order now. Let's do this in two different colors. Let's have blue be U and red be V. Now it's been switched, which means that this is the same thing as V dotted with U. How would you see this? Let's write one more step, because this would be V1, V2 dotted with U1, U2. Hopefully you can see how multiplying those two together would give you that right up there, which is the same thing as V dotted with U. So does the order of the dot product matter? No. U dotted with V is the same thing as V dotted with U. Just like how, this is called the commutative property. Just like with numbers, A times B equals B times A. It works the same for the dot product. Okay. So let's do a second property. What would you like U dotted with V plus W to be equal to? Like, ideally, what would you like the dot product to do?
Distribute?
Yeah, and it does. U dotted with V plus W is the same thing as U dotted with V plus U dotted with W. This is the distributive property. So you could sort of think of it as you can distribute it, or you can go use it to go the other way and to, like, quote unquote factor, although we don't call it that. But the fact is you can. This one's really interesting. So C is going to be a scalar. So if you have a scalar times U dotted with V, what you can do is, so do you see how it's this is a scalar times two vectors being dotted? There's several ways that you can break this up. You could first do the scalar times one of the vectors and then dot it. Or you can multiply the scalar by the other vector and then dot it. But notice that there's still a dot product for each of them. Dot product, dot product. Scalar, scalar. This one's called the associative property. Not that you need to know, but I'm just telling you. If you ever take linear algebra, they go over a lot of this in way more depth. And you have to, like, memorize them and stuff. Here, you just need to know how to use them. Okay, the last property is pretty cool. It's what happens when you dot something when it's with itself. This one's actually really cool. So let's just go through and calculate it. So I'm gonna have v1, v2 dotted with v1, v2. Which means I'm gonna have v1 squared plus v2 squared. And I'm going to write something on the side here. If you want the magnitude of v, what would you do? You would take the components, square them, and add them together. And then take the square root. And if you look, this matches the inside of the magnitude. So what is this equal to? What's the only difference between the two things that I've highlighted in red?
Magnitude squared.
Yeah. If you take a vector and dot it with itself, you get its magnitude squared, which is really cool. This gives you a really quick way to calculate the magnitude. So if you dot product something with itself, you get the magnitude squared. Boom. Okay, these are really helpful because like sometimes you'll need to calculate something and like you'll use the rules. Usually, like it's really helpful to know that the order of the dot product doesn't change anything. The distributive property gets used a lot, like in calculations. The associative property, sort of, not so much. And the fact that when you dot something with itself, you get the magnitude squared, you end up using like a lot of the time. Like a crazy lot of the time. Like sort of surprisingly a lot. It shows up like all over the place. Let's see. We are done with the dot. Actually, yeah, we got one more thing to cover on the dot product. Okay. So let's use the dot product to figure out something cool. Let's talk about projections. Projections of one vector onto another. Okay, so let's say you have a vector v and here I have a vector u. Boom. We want to talk about the projection. That's what the proj is. Of, oh shit, I drew this wrong. Projection of v onto u. Okay. The projection. Okay, I do it right. There we go. This is the projection of u onto v. So you could put like a parentheses right here. So the thing that's being projected is in the parentheses. What does it mean to project u onto v? It means that you drop an altitude and you get this vector right here. The thing in white is the projection of u onto v. So you can imagine, so what this is you get a vector in the same direction as v, and the magnitude is determined by the shadow u casts on v. Like if you imagine you've got like a little flashlight right here. Does it make sense? Like the light would come down. Right, do you see how the light would hit here? Like all of those things of light would go there, so you get the white part would be the shadow. Okay, so how do we do this? So notice, because I dropped an altitude, I have a right angle. So right here, this is my projection. Actually, let's make this a little bigger. So here's my projection of u onto v. There's that altitude that I dropped, and then here was my u. Okay, this is my u. Okay, I have a right triangle here, and I actually know one of the sides. What is the one side that I know? I know the length of one side only. Which side is that?
U.
Yes, this is magnitude u. Hooray! There's one other thing that I can label on the triangle. What is it? That I can calculate.
Do you know the angle too?
Yes! Remember how we started with figuring out the angle between two vectors? Because...
So you can use the hypotenuse formula.
Yeah, exactly, because I know that the projection of u onto v is the same direction as v. So I know that my angle is equal to the... Okay, wait. Let's make sure I write this correctly. Oh, well, actually, let's not say that. I have a better thing to say. Okay. What is the cosine of theta equal to? That's a better question.
Is the bottom size of u?
Yes. The bottom size is the magnitude of the projection of u onto v, that's the bottom side, divided by the magnitude of u, which means that the magnitude of u times the cosine of theta is equal to the magnitude of the projection of u onto v. So I actually now know what this length is, the projection of u onto v. I know that length now. So I actually have two lengths. I know the length of this one, and I know the length of that one. So it's like, hooray! Okay. And there's another change I can make. I actually have a formula for this. I know that the cosine of theta equals, because remember I have v and I have u, and I have a formula for the angle between them. Cosine of theta is equal to u dotted with v divided by the magnitude of u times the magnitude of v. So I'm going to make that replacement. The magnitude of the projection of u onto v is equal to the magnitude of u, and then I'm going to replace cosine theta with that thing over there, which is u dotted with v divided by magnitude u, magnitude v. So this is actually nice. I now know what the length of that base of the triangle is, only in terms of u and v. And I can now actually write what the projection of u onto v is. So I know that the projection of u onto v is a scaling of v, right? Because if you look at this, remember, v and the projection of u onto v have the same direction. So because they have the same direction, the projection of u onto v is just some number times v. How do I know this? Let's write, we know, let's actually type it. Since the projection of u onto v and v have the same direction, we know that the projection of u onto v is a scalar multiple of v. Okay? So what that means okay, wait, I hear a show in the background. Can you mute yourself? You use another person for fun. I'm gonna mute you. Sorry. Okay, we're on our last little step here. So you need to multiply the vector v by the appropriate scalar so that you get this length. So if you take the magnitude of both sides, so this would be like this. So that means that the magnitude of v is equal to the magnitude of the projection of u onto v divided by k, which means that the projection of u onto v will be equal to u dotted with v divided by the magnitude of v squared times v. Boom. So if you ever want to project one vector onto another, in other words, basically find a shadow, that's the formula you need to use. Oof. Okay, that was a lot for the end. We'll probably talk about this again next time. I'm sort of hoping